Hello viewers, welcome back to our series of lectures on Unit 1 of the paper CH202 Organic Chemistry 2. In this series we have so far talked about UV spectroscopy, and today we will take up a new spectroscopy, that is IR spectroscopy. In this session what we are going to do is we will start by defining what do we mean by IR spectroscopy. Thereafter we will see that what is the importance of IR spectroscopy in terms of structure determination and things like that. We will just try to briefly touch on that. More of it will come in the later sessions. Having done that, we will move on and see that how do we model molecular vibration. We will try to use Hooke's law and try to work out, rather try to share an expression which gives us the vibration frequencies of a molecule. Thereafter, we will look into how does the spectrum look like and what are the characteristics of IR spectrum. Then we will see that what kind of necessary conditions are required for a spectrum to be observed, for IR spectrum to be observed. Having done all that, we will try to sum up what we do in today's session. Okay, let's make a beginning by asking ourselves what is IR spectroscopy. IR spectroscopy basically is a study of the consequences of interaction of electromagnetic radiation in the IR region with the molecules. Spectroscopy in general we know is the interaction of radiation and matter. When the interaction happens to be of belonging to the IR region of the electromagnetic spectrum, we talk it to be an IR spectroscopy. Now what happens is, in case of IR spectroscopy, when we take radiations in the IR region and interact with molecules, this causes the transition amongst the vibration energy levels of the molecule. That is why this is also called as vibration spectroscopy. One more thing we have to keep in mind is that the spectrum which comes as a consequence of this interaction is called as IR spectrum or vibration spectrum, just to identify the fact that these are the vibrational motion which is involved in the process over there. Now let us see that what is this IR region of EM spectrum. I am sure that when we talked earlier about EM spectrum, we know that EM spectrum refers to a wide range of radiation there of different frequencies and all. But when you talk about the IR region is a very small region in the whole electromagnetic spectrum there, and this actually is placed at next to the visible spectrum here. I mean, this is my visible range here, that is typical VIBGYOR from violet to red, and it is just next to the red. That is why it is called infrared, beyond red, and the wavelength of this region are more than that of the visible range here. What you further see is that this whole region, the infrared region, actually extends from about 10 centimeter inverse to 12,500 centimeter inverse. It is a very broad region for that matter. This is an expanded version of the same thing over there. Now if you go a little further into this, we find that this IR region actually is further divided into three components there. One is called as a far IR region. This extends from about 10 centimeter inverse to 200 centimeter inverse. Basically this is far from the red end of the visible part. Now in this region what happens is, the molecules which contain heavy atoms and things like that, they are the ones which absorb radiation in this range. Typically for an organic chemist, this region is not of much interest. Similarly, the second region what we have is called as a near IR region. This is the one which is just next to the red in the visible range, that is about 12,000 to 4,000 centimeter inverse. Here again simple molecules like water and carbon dioxide etc. absorb radiation there. This again does not really fall in the domain of an organic chemist to use it as a regular tool here. This is used by environmental scientists and all, but for organic chemist point of view, this is the mid IR region, that is extending from about 4,000 centimeter inverse to about 200 centimeter inverse. That is the broad range in which the organic molecules absorb. So that is of interest to an organic chemist, where the vibration what we see here, they are the ones which will be made use of in working out the information about the molecule in question over there. Okay. Now let us look at how does a spectrum look like. The IR spectrum looks something like this. It is the one typical spectrum shown over here. So what you see is, first and foremost, you see that the x-axis, typically we know that in any spectrum x-axis has to be some measure of energy, and in this case of IR spectrum we use it to be centimeter inverse. In UV spectroscopy we had wavelength here. Here also we talk about wavelengths, but normally we don't. We do indicate wavelengths over there, but normally we do not communicate in terms of wavelengths. We communicate, typically IR spectra are taught in terms of centimeter inverse or the wave numbers there. That's one point of differentiation between UV and IR here. And second thing is on this alternate axis here there, what you find is we have got percentage transmittance here as against absorbance in case of UV spectroscopy there. They are typically, both of them are absorption spectra, but in this case the way they are kind of presented, the two are different there. So in this case the spectrum actually is like this, it comes downwards here. In case of UV, what we had was, we had spectra which will be going upward like this. So from 0 onwards, in this case what we have is a transmittance here. It is just the reciprocal of absorbance there. So there are few points of differentiation between the UV and IR here. Another thing probably which is obvious from here is that in case of UV there were only few bands, there were very broad bands there, 2 or 3 or few bands over there, whereas in case of IR you got a large number of bands coming there. So that is as regards the spectrum, how does it look like there. Now let's look at what are the characteristics of IR spectrum. From IR spectrum point of view, IR spectrum, as we just saw, it consists of a number of signals, or typically they are called as bands. It's a broad spectra. They are not line spectra like in atomic spectrum there. And secondly, these so-called signals, they arise from the absorption of IR radiation by the different possible vibrations in the molecule, because the molecule is vibrating all the time. And since a given molecule may have a large number of say bonds in that, each bond is vibrating, some bonds are vibrating simultaneously and all. So all these vibrations are at different frequencies. So when the IR radiation is absorbed by each one of them, that will show up as a band in the IR spectrum there. That is one characteristic, that is we got number of bands over there. Another characteristic of IR spectrum is that these vibrations, this is not exactly a characteristic, but that is one convenient way of kind of talking about the spectrum. That is, we can talk about IR spectrum in terms of two broad regions. That means all these vibration frequencies what you observe in the spectrum, they are put into two broad groups called as skeletal vibrations and group frequencies. They are very useful in terms of the application part of it. We will talk about it in one of the future sessions over there. And just in this lines we can see that what are these two regions. Let us have a look at it here. This is my same spectra again. This region here, say about 650 centimeter inverse to about 1500 centimeter inverse, we have got what is called as a skeletal vibrations or fingerprint region there. And the region beyond it, say from 1500 to about 4000 centimeter inverse, what we have is, this is my group frequencies region. Here they are typical, the functional groups frequencies will be coming over there. We will talk more about it in the future sessions there. Let us continue and see that another two very important characteristics we have to identify in any IR spectra, and they happen to be, the first one is the intensity part. Let us look at this. This particular band here, the signal here is, it's an intense signal. You can see that it is dropping down extensively here. This is an intense signal, whereas this one here is a weak signal there. So that is one kind of way of looking at it, because when we talk about IR spectra, we talk about different bands coming there. So we tag them. This is an intense band, a medium band, or a weak band. Okay. So I have just given two things over there, a strong and a weak one. You can think of this to be some kind of, the bands here, they can be talked about as medium or moderate. Medium is used more often there. Another way of looking at the signals in IR spectrum are that this is a broad signal or a broad band. What you can see is this extends through about a large number of centimeter inverse here, whereas this signal here is a sharp signal. So they are the kind of things which you have to communicate there. Okay, let us move further and see that how do we rationalize these characteristics there. The first characteristic is intensity of signal. Intensity of signal basically is related to the dipole moment of the bond here. But what happens is, if I have a bond, say a given molecule I am taking there are two things I am taking here. One is a carbonyl compound, one is a alkene kind of a molecule there. So what you see is it has a CC bond here, this is called a CO bond here. This bond is more polar as compared to a CC bond here. So what will happen is, this bond has got high dipole moment. So when it got a higher dipole moment, when it vibrates, it gives me very intense change in the dipole moment there. So this will give me an intense signal. So a carbonyl signal is more intense as compared to a carbon-carbon double bond signal there. It is just schematically shown over here. That means this will be a very sharp kind of signal and a shorter in intensity signal. This will be a CC bond here, whereas this is a very sharp and intense signal that is for a carbonyl group. Just for sake of understanding here, that is anything which is more polar will give a more intense signal there. That is one. And as regards the width of signal, there are a number of parameters which actually determine the width, but generally the spectra, as we have been seeing so far, that is the spectra, the signals or the bands are quite narrow, but some of them happen to be quite broad, and a number of factors are the ones which make the signal broad, and the most common factor happens to be the hydrogen bonding here. In case of hydrogen bonding, what happens is, we know that a hydrogen bond can be represented as follows, wherein this X and Y happen to be two electronegative atoms, so it could be oxygen, nitrogen or a halogen or so on and so forth. So, when that happens, we know that some kind of a charge separation comes into play, and because as a consequence of the hydrogen bond formation, we find that this XH bond here actually becomes weak. Since it becomes weak, it gets slightly extended. When it gets extended, the strength becomes less. As a consequence, what happens is, one is the strength becoming less, secondly, this is a dynamic, it is not that it has become fixed in certain orientation there. So, this hydrogen bond is slightly dynamic. As a consequence, this bond strength actually keeps varying. As a consequence, a number of different frequencies are there for the band there, and as a consequence, the spectrum becomes broad here. Okay. Now, so we can just have one look at it, that how does hydrogen bonding affect the spectrum here. It is just a schematic representation here. So, suppose I am looking at a molecule, a organic compound having a functionality which can get into hydrogen bond, say typical in alcohol molecule there. If I take the spectrum of that alcohol at high concentration, I find that this gives me a very broad band around about 3300 centimeter inverse. And if I dilute it with some kind of a solvent like say CCl4, which does not absorb in this region and also does not let the hydrogen bonding to be there, it breaks the hydrogen bond in a way. So, we find that in the moderate concentrations, we find that this becomes slightly weaker and a sharp signal starts coming here, which refers to a free OH group there, that means which is not hydrogen bonded, and this is the one which is hydrogen bonded. So, both the components will be shown over there. If I further dilute it, we find that there are this band of free OH becomes very intense, and that of the hydrogen bonded component becomes weaker in this thing. So, that is how we can see that IR spectrum can help us work out whether the system is hydrogen bonded or not. That typically can be ascertained in terms of varying the concentration and observing the spectra. Okay. Now, let us see what is the importance of IR spectrum. We have just seen what is the IR spectrum, and then how do we, what are the reason behind getting IR spectrum. Now, let us look at how do I make use of this. Some points of it I mentioned earlier also. Let us continue with that. One and very important use of IR spectrum is, that is the identification of different functional groups in the molecule. That is, we will be using group frequencies region. You remember that about 1500 to about 4000 centimeter inverse, that region, the bands which are coming there, they will be put to use to find out the functional groups in the molecule. That is very common use for an organic chemist. Secondly, another very significant, more so for a kind of a person who is getting into active research using IR spectrometry, is that we establish the authenticity of a molecule, and for that we use a fingerprint region. We will talk more about it at a later stage. So, there are two very important kind of an application of IR spectrum. Yet another is that we can differentiate very closely related molecules by using their IR spectrum, because you may have situation, say a molecule, say ethanol is there, and the isomer of it is dimethyl ether. So, they will have two very different kind of spectra. So, that can be used to find out whether it is an alcohol or an ether. So, that kind of applications, we will be talking about all these things at a later stage. Right now, I am trying to give you an overview of what kind of information can we get from IR spectrum. Okay. Now, having just talked in a capsule view about IR spectrum, let us look at the theoretical aspects of it. What is the basis of all these things, what we are talking about here? And as I just mentioned earlier also, that is, we are talking about IR spectrum, and IR radiation basically kind of alters or interferes or interacts with the molecular vibrations. So, what is a molecular vibration? How do we talk about it? Molecules we know that there is no molecule which is stationary. All molecules, all at all temperatures other than the 0 Kelvin, they are in constant state of motion there. So, no molecule is stationary for that matter. When they are in motion, they are executing a vibration motion there. So, they execute wide variety of vibration motions. That could be stretching, that means the band is stretching there, or it is bending motion, and there are a large variety of kind of vibrations which the molecules can execute. And then these vibrations actually have got characteristic frequencies which relate to the structure of the molecule. So, let us see how do I physically visualize a molecular vibration. A molecular vibration can be seen or visualized in terms compression and extension of two balls joined with a spring. Basically, I am trying to visualize a bond in terms of two spheres which are representing the two atoms, and the spring is representing the bond over there. So, if I just take two balls attached through a spring and try to pull it and then leave it, it starts vibrating. So, that actually can be seen as the way a molecular vibration can be visualized there. So, what you have is, as in this picture shown over here. So, this is the atom A, atom B, these two are linked together by a spring in between there. So, what can happen is, so we can stretch the spring. So, this gets this position here and here, or when we compress we get these positions there. So, we find that this basically represents what is called as a molecular vibration, the one way of looking at it. Another thing, probably we have a similar picture here. So, this is my normal bond here, the two atoms here, they bond through a spring representing a bond here. Now, if I extend it, so that is my stretched position there, this is the compressed position there, and this represents the equilibrium bond length over there. So, that is the meaning of a molecular vibration here. When you talk about the molecular vibration in terms of two balls attached with a spring, probably it immediately gives an idea that we can try to invoke Hooke's law over here, because what does the Hooke's law say is that the restoration force is equal to minus k r minus r equilibrium. What it means is, suppose I have got a spring, the two balls attached to a spring, if I stretch it, there will be restoring force there, that will try to bring it back, or if I compress it, the spring will try to bounce back here. So, that is what Hooke's law talks about here, and the expression for Hooke's law is F is equal to minus k r minus r equilibrium. R equilibrium is the equilibrium bond length or equilibrium length, so to say, and this r is, whether it is a compression, it will be lesser, if it is extended it will be larger one there. So, F is my restoring force, K is the force constant, R is the internuclear distance here, and R is the equilibrium internuclear distance here. So, the direction of restoring force will be opposite to the field of the displacement. If I am trying to pull it out, force will be towards inside. If I am compressing it, force will be acting outwards there. Okay. Now, besides the Hooke's law, there is one very important formula which we have to bear in mind, that is the vibration frequency of the bond actually depends on two parameters. One is called as a force constant, that is that is why we talked about the Hooke's law here. That means force constant basically is the restoring force. That means in terms of our molecules, this basically refers to the strength of the bond. So, K is a measure of strength of the bond called as a force constant here, and this mu is nothing but my reduced mass, that is the reduced mass of the molecule here, and which is defined as, we all know that mu is equal to m1 m2 divided by m1 plus m2 here, and of course, we got 1 by 2 pi as a constant of multiplication here. So, that means omega oscillation, the oscillation frequency or the vibration frequency of a molecule is given by the following formula, 1 by 2 pi square root of k by mu in terms of units of hertz here. But normally, as I just been talking about earlier also, that is in case of IR, we are using units as centimeter inverse. So, what do we do is, we divide this by C. So, when I divide by C, my units now become centimeter inverse, and the symbol here becomes omega oscillation bar here. Normally, we just skip this bar and just call in terms of frequency, but we actually are referring to a wave number here, because the units happen to be centimeter inverse. So, this 1 by 2 pi c k by mu is the formula which has to be used very often. You can use this if you are talking in terms of centimeter inverse, and this one if you are using in terms of hertz there. Let us see some examples here. So, what you find is, from that formula is very useful in terms of how to make use of IR spectrum is just some simple kind of correlations here. what you see is as K increases, you see that carbon-carbon single bond is there, a double bond, triple bond. So, since all these molecules here have got same value of mu, because the two atoms happen to be same, mu is the constant here. So, in this case K is less, larger, still larger, and so is the vibration frequency here. So, 1200 centimeter inverse, 1650 and 2150. Similarly, we can think of CN bond here, C double bond and C triple bond, and here again you find that the same trend is there. Or we can take another example here, wherein what we do is we keep one atom constant here, say carbon constant here, we got hydrogen, carbon, oxygen, chlorine, and we find that as the second atom's mass becomes larger and larger, the reduced mass increases. As mu is increasing, we find that the vibration frequency goes on decreasing there, because there is a inverse relationship or a reciprocal relationship with the mu, and there is a direct relationship with the force constant K over here. Okay. Now, let us see what is a necessary condition for observing IR spectrum, because we know that we talked about UV spectrum. So, in that case practically all molecules will be able to absorb radiation in the visible or UV range over there, but in case of IR spectrum all molecules do not interact with radiation in the IR range. Maybe some molecules do not interact at all, some molecules, some of the vibration modes do interact, others do not. So, what is the requirement here? The requirement here is that the vibrating molecule must be associated with a fluctuating or an oscillating dipole moment. That means, if a molecule is vibrating, in the course of vibration the dipole moment must change. Let us see, and if that to happen, all polar molecules will show IR spectrum, because a polar molecule has a dipole moment, and if it vibrates the dipole moment is bound to change, and they are going to show IR spectrum. So, we see that this hydrogen here is non-polar, it does not give us IR spectrum, whereas HCl, which is a polar molecule, all of us know that this gives me a IR spectrum. This is one simple example to quote over here. And the reason for this is that if I take a vibrating molecule, this is vibration modes of carbon dioxide here. So, what you find is that in this case we find when this molecule vibrates in this particular mode here, we find that the dipole moment is changing continuously. Since it is changing, so this mode of vibration will be seen in the IR spectrum. So, this mode of vibration will be IR active, so to say. Let us see what do we mean by saying that the molecular vibration should be associated with an oscillating dipole moment. Let us understand that in little more details now with an example of a carbon dioxide. A carbon dioxide molecule, we know a molecule per se does not have a dipole moment, but some of its vibration modes are IR active. How does that happen? How do we explain that? Let us look at it. That to be understood, we have to see that what are different kind of vibration a molecule can execute. One typical vibration of carbon dioxide, this A here represents carbon, and these two small balls here are my oxygens there. So, this is my CO2 molecule there. Now, in this mode of vibration, this is called as asymmetric stretching or antisymmetric stretching. In this case, what happens is, if you look at, this is my CO bond here, this is second CO bond here. So, what you find is that this CO bond is undergoing contraction. We can see that these two atoms are coming closer. This A is coming towards O, carbon is coming towards oxygen, oxygen is coming towards carbon. There is a contraction here, and if you look at this arrow and this arrow, they are going away from each other. That means, this is undergoing expansion there. So, this is expansion, this is contraction. So, one bond is contracting, one is expanding. That is antisymmetric or asymmetric stretching. Symmetric stretching you see is that simultaneously this bond is expanding, so is this bond. When this will contract, this also will contract. So, this is symmetric in nature, and this mode actually is called as a bending. This is in plane or out of plane bending. So, this is seen as a kind of in plane bending. In plane bending means is that is, suppose this is my carbon atom, this is one oxygen, another oxygen here. So, okay, this is my carbon here, the center here. So, this is the kind of motion I am talking about. That means, this is the plane of the molecule. So, these two oxygens are going up, coming back, coming down, and so on and so forth. This is in plane, within the plane of the molecule. And second possibility of bending motion is the same molecule, now it is bending like this. That is, it is stationary like this, it comes towards you, comes back here, comes to me, back, and so on and so forth. So, this is out of the plane. So, there are two bending modes and two stretching modes of carbon dioxide. And the stretching modes, one happens to be symmetric, one is asymmetric, and bending mode, one in plane, one out of plane there. Okay. Now, let us see that which of these motions are going to be IR active there. Let us look at it first, the asymmetric stretching motion. Now, what you see is that this is my molecule of carbon dioxide, this is C, 2 oxygens here. So, what do I do is, let us go here to next step here. So, we find that this bond has got expanded, whereas this has got contracted. Go further, it comes back to normal position there. Now, this gets contracted, this gets expanded, comes back to normal there. If I come the other way around also, the same thing is happening. From normal position, this is stretching, this is contracting, and so on and so forth. So, you find is the dipole moment of this bond and this bond, they are directed opposite to each other, they cancel out. So, there is no net dipole moment here. But when you come to this molecule, this orientation here, or this particular position here, we find that the dipole moment of the two are still in opposite directions, but the magnitudes are different now, they do not cancel out each other, there is a net dipole moment there. This becomes 0 again, this becomes net in the opposite direction. So, you find that as this molecule vibrates in terms of asymmetric stretching mode, we find that there is a change in dipole moment continuously there. So, this mode of vibration will be interacting with IR radiation, and this will be observed in the spectrum there. Okay. That is the meaning of a mode being active here. Let us look at stretching, symmetric stretching here. We find that this is the normal position of my carbon dioxide, this is contracted one, further contracted. So, in none of these orientations here, or if I just take this as stretching one, further stretched over there. So, we find that in all these possible situations here, we find that the dipole moments of the two bond moments, so to say, they are opposite and cancelling, they are equal and opposite to each other. So, they cancel out, there is no dipole moment, and this mode happens to be IR inactive. Then the third mode we can think of, that is the in plane bending here. So, what you are seeing is that this is a normal molecule here to begin with. So, the two bonds bend in given direction, there will be a net dipole moment like this. Then when they come to normal position there, it is 0. Now, they bend in the opposite direction, the dipole moment is in the opposite direction now. So, there is a continuous fluctuation of the dipole moment, because these motions are very, very fast. It does not happen that very slowly it is happening, it is a very, very fast motion, and we find that there is a continuous change in the dipole moment there. So, this is generating an oscillatory dipole moment, and this oscillatory dipole moment interacts with the IR radiation, and what you get is a spectrum as a consequence. Let us look at the fourth mode of vibration here, normal molecule here. So, we find that this plus, that means this carbon atom is coming towards you, whereas these two oxygens are going away from you. So, there will be net dipole moment in given direction there. This again becomes 0. In this case, carbon is going away from you, and these two, the ones which are given as positives here, there are two oxygen atoms which are coming towards you. So, here again we find that dipole moment changes. This mode also will be IR active. So, let us sum up what are these modes here. We find that asymmetric stretching is IR active, but symmetric stretching mode of vibration of carbon dioxide is IR inactive, and the two bending modes, both of them happen to be IR active there. Let us sum up what we have done today. What we have done today is, we started by defining what is IR spectroscopy, and then we described the region of IR part of the electromagnetic spectrum there, and we found that there are three different regions: far IR, near IR, and mid IR. And then we talked about the relevance of each region of spectrum in terms of their suitability for an organic chemist or otherwise. Then we outlined the importance of IR spectroscopy, and having done that, we discussed the modeling of molecular vibrations and the expression for vibration frequency, and we saw in terms of the expression here, that is the vibration frequency to be equal to 1 by 2 pi square root of k by mu is a very, very important expression, because that relates the vibration frequency with two important parameters: the force constant or the bond strength, so to say, and the reduced mass there, and we showed some data to correlate the two. Thereafter, we explained the characteristics of IR spectra, that is the different bands what we get there, they are either intense band or weak signals or of a medium type, or we talk about a sharp band or a broad band and things like that. That is how typically we communicate about the signals in IR spectrum. And then thereafter, we discussed towards the end the necessary conditions for observing IR spectrum, and that happens to be that the molecular vibration must be accompanied by the change in the dipole moment there. In the next session, we will continue with our discussion on the basic aspects of IR spectrum. We will take up more issues, more fundamental things like what are the kind of transitions possible in a molecule, and what are different possible modes of vibration there in a given molecule, how many of them are there, and what kind of transitions are allowed, what are not allowed, and then how do we actually record an IR spectra. So, all that will be taken up in the next session there. Thank you.